Hello, everyone. Welcome to another episode of Q&A about history of science and technology. So let's see. I think we have a number of questions um, saved up here. Uh, hmm, right. Well, Graham is asking, just as language has developed and changed throughout history with new languages, dialects, and accents, do you think Wolfram language will grow in that way to be more regional and categorical, like math versus physics and so on? That's not the goal, and that's not what's actually happened over the last 38 years or so. The overall objective is to have kind of a computational infrastructure for describing the world, and to do that in a way that is kind of uniform and coherent. I think it's interesting to see some of the things that have happened. For example, there are concepts that back in 1986, 1987, when I was first designing Wolfram Language, there were concepts that were very hard for people to understand. Things about functional programming, things that related to even representations of different kinds of things with images and things like this. And as time progressed, those things became more familiar, and they became things that were realistic to put into the language. I mean, kind of what we're interested in doing is taking sort of the raw capabilities of computation and making a bridge between those and uh, and what um, and what exists and what we humans can actually think about. One of the things that really helps us is the human language, like English, for example, that we get to use human language as a way to explain what the functionality of Wolfram language actually is. So, for example, we can say something like nest list, and there's a notion of nesting, and there's an idea of a list, and people already know what those concepts are. If we had to call nest list, function 373, it would be much harder to understand what was going on. People would not be able to do it. Sort of an interesting tale along these lines. Mathematical notation invented, what, 400 or 500 years ago, mostly, plus signs, equal signs, things like this. It came in quite gradually. Those things were sort of introduced, over a long period of time. There was an attempt to make kind of a math notation-like play for computer languages done by a chap called Ken Iverson, a language called APL that kind of originated at the beginning of the 1960s. And Ken Iverson told me his goal was to have things analogous to plus signs and equal signs and so on in for computer language, but to do that with notation. So, for example, he had kind of this whole special keyboard with special characters, with kind of triangles and lines through them, and things like row-like characters and iota-like characters and so on. It was really a thing where they were kind of notational glyphs that represented computational kinds of things. It was not a success. People didn't manage to understand 50 new glyphs that represented different kinds of computational operations. Now, some of those operations, things like, for example, what's range in Wolfram language was iota or an iota-like character in APL. And I think, oh gosh, what was the map operation? I don't remember what it was. The thing that turned out to be really valuable in Wolfram language was leveraging the fact that people already know a term like range or like map. They already know those terms, and therefore, when they show up in our language, it's clear what they mean. I have to say, when I built SMP, forerunner to Mathematica and Wolfram language, I built starting in 1979. In those days, one of the kind of practical constraints was typical people who might be using a system like that didn't know how to type. They were typing, one finger at a time and so on. And so it was a big kind of, it was important to have short command names because ideas like autocomplete were far in the future. That we were dealing with dumb terminals where you just typed a character and, uh, and that would get sent in. It wasn't something where there was feedback to the terminal and so on. Even there was one was using SMP one could use from a teletype, literally a thing that was producing, pieces of paper coming out of it, and one was typing characters on that. So it was kind of a different world in terms of what one could do with kind of the names of functions and so on. And in SMP, I used short names for functions, and that made SMP code very hard to understand. If you saw, I can't think, oh gosh, what were some examples? AR for array. Okay, what does AR mean? Who knows? Something, all the various mathematical functions being named. I think those were a little bit longer, like BESJ was a Bessel J function. There were functions. I think the king of weird function names in SMP was Rex, like the Latin king or the Tyrannosaur version. A Rex was a random expression generator, but if you saw that, in a piece of code, it's like, what on earth does this mean? So I had the experience of trying to use short kind of shortenings of English words as command names in SMP. It was not very successful there. For APL, it was kind of a disaster, and it really damaged the use of the potential for APL. APL has a lot of very interesting design ideas about array programming and so on, many of which I've made use of in Wolfram Language, but APL itself was really never successful in a broad scale. I mean, as happens often, there were a small number of finance companies, for example, which sort of exotically chose to use APL for a lot of things, but otherwise it was not very widely used. And I think the strange character set didn't help. APL was Ken Iverson had worked at IBM, and APL was sort of connected with IBM, which was at that time the world's by far largest computer company. And IBM had to develop, special APL keyboards so people could type APL and so on. Of course, in modern times with soft keyboards and all this kind of thing, it's a bit of a different story. But back in the 1960s and early 1970s, that was the only way to solve that particular kind of problem. It's worth realizing that in those days, the standardization of characters, computer characters, things like ASCII, that was not yet standardized. IBM was pushing a thing called EBCDIC, which was kind of an alternative way of encoding characters that had different special characters. I forget exactly what it had. I don't know whether it had a hash sign, for example, in EBCDIC. I think it did not. So there was a time when there were sort of different character sets, and the APL character set was such a character set. It just didn't happen to make it. So in any case, back to the question of sort of the evolution of language and it's the evolution of computational language, like Wolfram Language. I mean, I guess Wolfram Language is really the only serious example in modern times of a true computational language. There are many examples of programming languages which try to sort of describe the operations of a computer. What Wolfram Language is trying to do is to describe the way the world is in computational terms, a somewhat different objective, where we end up right now with about 7,500 different built-in functions. Typical programming languages are dealing with a few tens of primitive operations and then various kinds of libraries that add on to that. So I think the main driver of kind of change in Wolfram Language, is the 0th level driver is things we figure out that we can kind of represent in computational terms, adding on to the language. The other driver is ambient understanding of things that makes it possible for us to use terms that weren't there before. So, there are plenty of things to do with the web. Wolfram Language was first developed before the web was a thing. In fact, in a footnote to history, and when Mathematica, now Wolfram Language, first came out in 1988, one of the computer systems that it was announced to be on, although that computer hadn't yet shipped, was the Next computer, which was Steve Jobs' project between his time at Apple and his later time at Apple. The Next computer was particularly aimed at sort of education, research, development kinds of areas. We made a deal for Mathematica to be bundled on every Next computer. Mathematica came out June 23rd of 1988. The Next computer, I think, came out in maybe October of 1988. In any case, one of the one of the places that wanted to, so the calculation was more people will buy Next computers because it had Mathematica bundled on it. And for us, it was like, well, we get paid for every computer that got shipped, whether or not people actually used the Mathematica. As it turned out, it was a good deal on both sides. And a lot of places ended up buying Next computers, I would say almost irrationally, because they got Mathematica for free on those computers, even though perhaps the price of the whole thing of the computer was actually more than it would have cost them to buy a Mac plus a Mathematica software system. In any case, one of the places that did that was CERN, European Particle Physics Research Operation, and the theory group at CERN got a bunch of Next computers to be able to run Mathematica. The person who was the administrator of that network was a chap called Tim Berners-Lee, who ended up developing the web on that very network of computers. So in a sense, the computers that made the web possible were ones that were got in order to run Mathematica. So that's the way that I know for sure that the web post-dated Mathematica and post-dated the beginning of Wolfram Language. But clearly, there are many operations that we can now talk about in Wolfram Language that use the term web that didn't make any sense in 1988. Similarly, there are ones that use the term cloud that didn't make any sense until sometime into the 2000s when the idea of cloud computing came along. So, as the external language and technological language of the world advances, so we can add new constructs to Wolfram Language. The question of sort of the dialects and so on, and whether the kind of the big goal that I've had is to have this coherent way of talking about everything in computational terms, and not to have to specialize into, oh, that's for physicists, this is for mathematicians, that's for social scientists, etc. It may be the case that some operation or some construct is relevant mostly to chemistry, but it should be something that kind of uniformly fits in with all the other kinds of things we do in Wolfram Language. And that's part of the value, I think, is to make it possible to take something that's, a graph that is a chemical graph and have that be a graph that you can do other graph theoretic operations on, and so on. So that's not a place where we would like there to be any sort of separation between those two different areas. Now, I would say that everybody who uses Wolfram Language ends up using just in human language, there are certain words that any given person will use more often than others. So it is with Wolfram Language, and so it is with kinds of different parts of the language that people learn more and use more and less deeply. I would say another question that I've been long interested in is, how do you speak Wolfram Language? You can write it, type it, read it, and it is primarily a written language. But there are situations in which it would be nice to be able to just be able to say what you want in Wolfram Language. Actually, I had the experience maybe nearly a decade ago now, visiting. I happened to run into a group of kids in California who had been learning Wolfram Language. They were, I think, 11, 12-year-olds, things like that. And they had managed to find ways to speak Wolfram Language. They were a little disappointed that speaking it at their sort of full speed, I couldn't really understand what they were saying because I'm just not used to hearing it as a spoken language. But I've been long curious, is there a way of making sort of a version of Wolfram Language that can be spoken? You can certainly say things like, nest, 1 plus hash ampersand, comma X, comma 7 or something, but it's rather awkward. And the question is, the Wolfram Language is a tree-structured language. A good idealization, in natural language, a good idealization of natural language is kind of a grammatical tree where you have, something like noun phrase, verb phrase, noun phrase in English, and the noun phrase is then its own sub-piece that could be, adjective, adjective, noun or something, and the verb phrase could be adverb, verb, and so on. It's again a tree-structured kind of thing. In Wolfram Language, it's much more straightforwardly and rigorously a tree. In natural language, it's kind of roughly a tree. But the fact that in natural language, we can deal with this kind of tree structure and it feels natural to us. I mean, the the big red dog that jumped over the moon or something, over the blue moon. For us, it's not difficult for us to understand all this sort of subclausing of the big red dog, okay, noun phrase, quickly jumped verb phrase, et cetera, et cetera, et cetera. We don't think particularly, oh, there's a bracket there, there's a parenthesis, et cetera, et cetera, et cetera. Now, the truth is, when we use human natural language, we do lose it after a certain number of levels of subclausing. I mean, if I said the big, red, lazy, hungry, dog, after maybe 4 or 5 levels, it would be kind of hard to say what I was talking about. And in Wolfram language, as you build up these kinds of towers of functionality, you do end up quite often with deeper levels of nesting than we are used to in natural language. But I've long been interested in the question of how can we make kind of a flowing, kind of sequential way of saying Wolfram language using kind of the tricks that one has in standard human language. Different human languages have different ways to kind of define what different parts of a sentence are about, whether it's a tonal kind of thing, whether it's a thing with case endings, whether it's the thing with additional words and so on. There's ways to do that. And I've long thought that maybe it's by adding, extra words like open and comma. Well, open and comma are very directly the way it's printed, but the way it's written. But it would be nice to have something which sort of flows better, that is a speakable version of Wolfram language. But I consider that as yet an unsolved problem. My guess is that the spoken version would indeed have dialects and would indeed evolve in various ways, even though the written version is kind of locked down. And that's not unlike what's happened in a bunch of human languages. Sometimes in human languages, the written form comes after the spoken form, but in some cases, there's kind of a written form, and then the way it's pronounced or the way it's rendered is different in different dialects. Let's see. Jack is asking, when do you think language first became structured enough to support scientific thinking? It's a good question. I mean, I don't think there's been kind of of recorded language, and we only have language in historical times when things were written down, and that's kind of the origin, like of so many things of sort of earliest languages we have, are things like the Babylonian languages, things like Akkadian, Sumerian, things like this. It is my impression that those languages are sort of just fine to express scientific and logical kinds of things. I don't think there's been really, I think we could be speaking Akkadian now and we'd be able to say the kinds of things that we're saying. Now, of course, there's lots of vocabulary that's come in, but I don't think structurally there's a problem with those languages. I think I will say that a good friend of mine actually has the curious job, has had the curious job of is a professor in Oxford, and of giving sort of writing Latin orations that can be used for honorary degrees given to people in Oxford. And those honorary degrees might be people in computer science or molecular biology. And obviously, in the time when Latin was a natural language, so to speak, being a spoken language, routine spoken language, there weren't words for things like computers and molecules and so on. And so he has sort of the interesting challenge of making up kind of from what was describable in Latin, sort of renderings of things which we now know in modern times as chemical bonds or something like this. So it's doable, and I don't think there's anything sort of structurally lacking in certainly a language like Latin, or even in the earliest languages that we know from written records. It's an interesting question how human language evolved and whether at what point the kind of compositional structure of language, this whole idea of being able to have sort of phrases nested within each other, being able to put together different kinds of things, sort of an adjective goes with many different nouns and so on. When did that arise in the history of human language? Nobody knows. It's those things when it comes to animal communication, that's much more in the fetch sit one word at a time kind of setup rather than this kind of flowing compositional language that we have. I don't think we have any way to know when sort of compositional language arose in sort of the history of our species and so on. I think unlike kind of the actual sort of evolution of language itself, where we can kind of see, well, these languages, these Indo-European languages have lots of words in common and they're different from the words in, an isolate language like Korean or something, or Basque or whatever. We can kind of see the kind of tree of languages by looking at commonalities of words that emerge in current languages, but all current languages have this compositional structure. And although they do the composition differently, they might have case endings, they might have extra words and so on, but I don't think that's been significant. And I don't think that allows one to go backwards and kind of look at the phylogeny of language and see when those things originated. So I just don't think we know. And I think it's probably the case that it's tough to talk about the kinds of things that one needs to talk about for science or logic or whatever else if you're just in the one word at a time phase of language communication. Of course, the challenge then becomes, and I wrote about this recently because I was thinking about what if we go from sort of the cats and dogs with 1,000 times less neurons than we have to our 100 billion neurons to some entity with trillions of neurons or something, what kinds of additional things can happen in the structure of something like language? What comes beyond the compositional language that we know, and what kinds of thinking might be enabled by that sort of higher level language that are not things that we currently find familiar? And I think there is some indication of that. In fact, from what we built in computational language, in Wolfram Language, I think there's sort of an indication of a little bit about what that might look like. It's kind of the notion of, well, there are things that are just verbs that say, do this action. But then there are sort of higher level verbs that kind of describe kind of meta actions that you can take, that describe sort of how to construct an action. So even something like, I don't know, a function, I mentioned the function nest earlier. The function nest takes a function, takes something which does an action, like blurring an image, and it takes that action and it then does a higher level thing of saying nest that action some number of times. And that's not something that's very common for us to think about in traditional human language. I think it's something which becomes very natural when it's something that you're going to use in a computational language. And I think that gives one some indication of what it might feel like to have sort of a higher level of language enabled by kind of the sort of bigger brains or whatever else. I mean, it's a little bit humbling to think, if you're a cat or a dog and you're hearing all this complicated human language and you're hearing kind of a description of how to do algebra in that complicated human language, but your way of thinking about language is just kind of one word at a time. It's one meow at a time or whatever. It's kind of it's a bit humbling to realize you might just completely not get what's going on in compositional language. And at another level, it might be the case that there's sort of higher levels of language that are beyond what we humans have reached that we just completely don't get. Now, it helps when we can use computational language as a way to kind of build a formal tower where we can see how this piece fits onto this piece. We can see this tower built up. We can see how it's applied. That's our kind of crutch for getting to something which might be beyond what we can sort of naturally do just raw with our brains. Let's see. Question here from RBS. Was Leibniz's characteristica universalis basically a proto-ruliad? Was his main limitation the lack of hardware to execute simulations? So Leibniz lived in the late 1600s, and he was his main day job was being sort of a courtier and a figurer out of things. Like he was supposed to kind of write the history of the Dukes of Hanover and figure out, why it was okay for some particular duke to marry some person from some other family, et cetera, et cetera, et cetera, based on the long distant history of, yes, this bloodline was really okay for this or that thing. So he was a sort of a figurer out of things. And he was also, to some extent, a bit of a diplomat. I think he was, but he spent most of his life kind of hanging around the court of Duke of Hanover. He almost ended up coming to the court of, what was it, George the Third, maybe George the First. I forget. I'm losing track of my British monarchs there. But that person came out of the Hanoverian dynasty, but became the King of England. And in fact, one of Leibniz's very sort of unfortunate things was his kind of competition with Isaac Newton. Had Leibniz been brought to the court of George, maybe it was George the First, he would have been sort of higher in rank than Newton was in those days. Newton was by that time controller of the mint, but Leibniz would have been a direct, courtier to the king type thing. That didn't happen because at the time Leibniz was supposed to be finishing some history of the Dukes of Hanover, and he hadn't finished his homework, and so he wasn't brought to that court to go to England. And Isaac Newton kind of ran these rather somewhat, I would say, corrupt kind of investigations into the Leibniz-Newton controversy about the invention of calculus running through the Royal Society, which Isaac Newton was a big figure in, and was kind of pulling the strings behind the scenes, so to speak, to come up with the conclusions that were favorable to him. But in any case, Leibniz had sort of a long-term interest in kind of making things symbolic in a sense. His original PhD thesis had been about resolving legal cases using logic. And he was, I think, somewhat influenced by a chap called Ramon Lull from the 1200s, who had this way of kind of having these sort of physically made up wheels and so on, where you could kind of choose different possibilities for what would happen, and you could kind of combinatorially enumerate the possible things that would happen. Not so different from things like the I Ching and so on, but those were sort of ways to kind of take what happens in the world and have a sort of a formal representation of that. I mean, back from Aristotle and his predecessors in the development of logic, there was this idea of kind of the structure of arguments can be represented in a formal way. It's worth remembering that logic as we know it today, with ands and ors and nots and so on, and being able to be used in computers and such like, that was not the logic of Leibniz's time. The logic of Leibniz's time was syllogistic logic, where there are patterns of argument, like, all men are mortal, Socrates is a man, therefore Socrates is mortal. That's a particular syllogism, a particular pattern of sort of structured presentation of information that sort of makes logical sense. And back in the Middle Ages, people would memorize these different kinds of syllogisms. They had acronyms. There was one called Barbara, one called Celerant. I don't remember the others. They're easy to construct now from the kind of more mathematical structure of logic that we have from Boole from the 1830s and so on. But in those days, logic was memorizing these kinds of structures of arguments. And so for Leibniz, it was, could legal cases be resolved by just sort of putting these templates onto them to say there's sort of a symbolic representation of what happens in these legal cases, and that's how we can resolve them. Didn't work out for Leibniz. We're now at a time when computational law is finally starting to be a real thing, but that was 300 and something years later. But in any case, in Leibniz's time, Leibniz was also sort of in his diplomatic role. One of the things that was happening at the time was Latin was going out as kind of the uniform language of learning. Up to that time, sort of any serious book written intended for sort of the learned public will be written in Latin. But at the time, there was starting to be books written in English, French, German, and so on. There was sort of a fragmentation of learned works into those different local languages. I mean, notably, Isaac Newton, when he wrote in 1687, he wrote his Principia Mathematica, Mathematical Principles of Natural Philosophy, that was written in Latin. By the time he wrote his Optics, it was written in English. So that was right at the end of the 1600s, right when Leibniz was active, was just the time when there was a sort of break point between the uniform international Latin and the local languages being used. And Leibniz was sort of concerned about that and wanted to kind of uniformize the language of science, the language of sort of structured thinking in some way that was not specific to a particular human language. And so he was very concerned with things like mathematical notation. You know, he invented the notation for integral signs. He invented the notation for derivatives, d by dx. He said very immediately, he said, people will think you can cancel the d's, and that might be a problem, which is, of course, has been a problem for calculus teachers for the last 300 and something years. He also argued against William Outred's invention of the multiplication sign, saying people will confuse it with an X, which again has actually happened. But Leibniz was very concerned about this kind of standardization of notation for mathematics, which was just coming in at that time. He also had this idea of making kind of this universal language that would be sort of would transcend human language and be a way of representing thought. Now, there were other people who were also thinking about this kind of thing, like a chap called John Wilkins in England was doing this. They were trying to create what they were calling philosophical languages, languages that could represent ideas without being committed to particular human languages. Now, in making those philosophical languages, they were inventing their own sort of human-like languages. At the time, they was very confused between kind of the actual morphology of the language, the way it was written, you know, what kind of glyphs it would use and so on, and its semantic meaning, the kind of separation between semantics, the meaning of things, syntax, and even phonology of how it's spoken. The fact that those can all be really factored out and separated, that was a thing for a much later time. So at the time when Wilkins, for example, was making his philosophical language, he had its own script and everything else, made it even more inaccessible, so to speak, than it might otherwise have been. In any case, Leibniz kind of had this idea of this universal language that could represent thought in this kind of almost symbolic way, in the way that was kind of had the structure that he was imagining would be a mathematical notation, he was imagining would be these templates for logic and so on. He never really managed to get that far with that. He tried to convince some Duke of Hanover to create a library that would sort of have knowledge encoded, presumably in this kind of a universal language. It was kind of a Wolfram Alpha play a few hundred years before Wolfram Alpha. It didn't really get off the ground, like many of Leibniz's projects didn't really get off the ground. Now, how that relates to other kinds of things that Leibniz talked about. I mean, Leibniz did a lot of work in philosophy, and I've always found his philosophy quite hard to understand. I mean, there's sort of a direct line from Leibniz to Kant, and that direct line, I think, very much leads to ideas like the Ruliad, and very much to our modern ideas of space and time and the role of the observer and so on. But for Leibniz, there were a lot of things that I've always found very hard to understand. Leibniz had this notion of monads, that everything would consist of monads. One of the things very important for Leibniz was the notion of sort of souls, and where do souls come from? It's worth understanding that this notion of a soul, that's pretty ancient in theology, is a notion of something that there is a thing to brains that isn't just the wetware of the brain. There is some kind of eternal kind of engram of thinking, which in modern times we would think of as computation, but in earlier times it was this thing very much tied up with religion that was the soul, this thing sort of that is an engram of thinking independent of the actual hardware of brains. And as an engram of thinking, it is inevitably eternal, just as we might say, you know, this algorithm we wrote, it's an eternal thing. The fact that it does not persist in the RAM of our computer for very long is not really relevant. There is an eternal version of it. But Leibniz was very concerned about sort of how the soul, whatever that might be, emerged in things. And he had this idea. He didn't realize that sort of soul could arise from non-soul. He didn't realize that inanimate matter could be could sort of be aggregated into a brain that could think and so on. So for him, his monads, which were elements of everything, they're sort of his ultimate atoms, were also things that had little fragments of soul in them, because he didn't understand the possibility that one could have soul emerge from non-soul. So that makes what he talked about with monads really hard to understand, because that's kind of not the way we think about things. For example, for the ruliad, we imagine that the ruliad is ultimately made from eames, kind of atoms of being, atoms of existence, and that there is an atom of existence. It's just an atom of existence. It's a thing without kind of any structure, without anything other than its identity and its distinction from other atoms of existence. That's rather different from Leibniz's monads, which were in a sense kind of the whole universe packaged into this one atom, and then the universe made from many such atoms. So a slightly different kind of idea. But the notion that Leibniz had that it should be possible to sort of make a symbolic representation of everything, that's certainly a notion that I've tried to continue, and maybe we are getting closer to being able to complete the vision of kind of having this computational, formal, symbolic language that represents the kinds of things that we humans are interested in talking about. Let's see. A question from Graham here. Do you think linguistic evolution behaves like computation, simple rules branching over time into complex forms? How does language evolve? How does language emerge? I do think that a bunch of the ideas that we've seen, I've worked on the last year or so, about biological evolution and kind of the way of thinking about biological evolution as a computational process, excuse me. I think those ideas are applicable to linguistic evolution. I mean, the thing that's always interesting about sort of linguistic, what is language? What is it doing? It's taking all those random nerve firings in our brains and finding a way to package up the important aspects of what's going on in there, or at least the aspects we think of as important, in a way that we can communicate them to another brain. I mean, as I'm talking to you, there are all kinds of random nerve firings going on in my brain. Those nerve firings are particular to the structure of my brain. If I were to pick up those nerve firings and hand them to somebody else and implant them in their brain, they wouldn't work because the brain is set up differently. And so we have to have a sort of transport layer to go from the innards of one brain to the innards of another brain. And that transport layer is primarily language. And so then the question is, well, what should be in that language? How should that language be able to recreate sort of a feeling, a thought from one brain in another brain? What does kind of the transmission channel look like? It's sort of interesting that in neural nets and machine learning and so on, in AI systems, there's this notion of autoencoders, where you're saying, we got all these different kinds of images of cats and dogs and everything else, and then we're somehow going to be able to get the neural net to sort of compress those images down to some representation that can then, which has sort of fewer bits in it, many fewer bits than the original images, but then we're going to be able to reconstruct those original images or something like those original images sort of on the other side. And that notion of a kind of an autoencoder that's kind of squashing down something to encode a thing to recreate the thing later, that notion of doing something like that is very similar to what language seems to be doing. And there's a good question of whether we can kind of recreate kind of the formation of language by seeing sort of the training of something like an autoencoder. And I think this question of sort of how does language sort of emerge by starting to take somebody's thoughts, communicate them to somebody else? How do you crush down, compress, package those thoughts so they are communicable? And it's interesting, I haven't done experiments on this. A number of other people have tried doing these about sort of how this can actually work, and does language of the kind we see with its compositional structure and so on emerge from sort of trying to push things into that in that way. I think it's an interesting possibility. I think it's very likely that something like that can work. The things I've done in studying biological evolution, where there's a certain fitness function, you're trying to get a structure which starts from its underlying rules, runs those rules, and then succeeds in, let's say, living for a certain time and then dying out. You're able to sort of tweak those rules progressively and adaptively over time to get more and more successful fitness for the organism. So a reasonable question is, if your fitness function is, can these two critters understand each other when they communicate in this way? What would one expect to see in the formation of that communication channel? What would be the thing that one would expect in that communication channel? That's a good question. It's something I've been interested to look at. I have not looked at that. I think that the question of, once you have a language and it's being operated in the context of society, how does it then evolve? I suspect that quite a bit of that is tied up with the evolution of society, and a lot of kind of the structure that we see in the thousands of languages, 5,000, 7,000 languages or something in the world. A lot of the kind of details of those languages are determined by a lot of kind of demographic, sort of geographical information, whether it's, oh, there's a mountain range here that separates these two different communities that have never had to talk to each other, or, oh, this community came in contact with this other one and that formed some kind of Creole language or something. And it's, there's a lot of sort of human geography that's affected the formation of languages. And I think that it's a question to what extent there are sort of universal principles of the way that languages evolve. I mean, the Grimm brothers, in addition to collecting fairy tales, also were trying to collect information about the evolution of languages in Europe, and that leads to things like Grimm's law, which is a law for the way that pronunciations evolve over time, and so on. And I think it's a reasonable question: is there sort of a universal evolution of language that's inevitable, or is it all determined by kind of details of society and human geography and so on? And for that matter, the creation of technology, because the new words that arise are often words where they either come from new sort of social structures, or they come from new technology, new discoveries, and so on. I mean, if we look at English, for example, there are certain constant progressions that I've certainly noticed. One of them is the smooshing of words. Back in the day, it was web space site. A few years later, website is a word. And that's a very common thing. I mean, I've always pointed out to our document quality assurance team that looks at documents, among them things that I write, and says that word is spelled wrong, or whatever else it is. I always tell them, when it's something which is a two-word thing, for example, it's like over time those words will smoosh, and we might as well be ahead of the curve and put website as one word rather than two. But that's an example of something which seems to be a progression that might be independent of, that might be sort of a natural progression. As soon as a word is used a lot, it tends to things tend to smoosh together. Of course, that's not always the case. I mean, in I don't know, in French, there's s'il vous plaît, for example, which remains as a almost four-word combination for the word for please, that hasn't smooshed into a single word. So although it's always said together. But I think but this question of sort of the evolution of language, I don't know to what extent it can be independent of the ambient evolution of society and of the kinds of things people want to talk about. Those are all things. The evolution of society is actually something that I'm very curious to study in sort of computational terms, and to sort of understand. There are various sort of progressions. So actually, one thing I mentioned about language. Language doesn't work if only one person speaks it. Language is a story of kind of a community where everybody has to speak the language, or the language isn't useful to anybody. And it's kind of this whole notion of kind of the uniformization of things, something where you might say, in a typical model in physics, it might be there's a gas and there's molecules, and every molecule is for itself bouncing around. But in fact, we can describe the gas just in terms of its overall pressure and volume, or something, for many purposes. So similarly, there might be things where If we look at the operation of society, for example, there are things where everybody's doing their own thing, but in the aggregate, there are things you can say about society. And in fact, the very possibility of having any kind of narrative of history, different people may disagree about what the narrative of history should be, but that there is a collective narrative of history that is even roughly sort of collective among millions of people is an interesting fact. And it's not unlike the fact that we can describe the important features of the gas in aggregate terms without having to describe what every molecule is doing on its own. And I think there is sort of a common thread between kind of the aggregate description of society and the possibility and utility of language as kind of this standardized way of communicating thoughts. But I haven't unraveled how that all works. Let's see. RBS is asking, was there a lost century of logic between Babbage and Shannon? Did railway or hydraulic engineers build Boolean gates without realizing it? That's an interesting question. So, okay, let's talk about several different things. So Boole was a contemporary of Babbage in 1830s, 1840s, that kind of time frame. Boole really took what had been this template-based syllogistic logic and said you can mathematicize it. Boole knew about algebra. He knew people like De Morgan, Augustus De Morgan, and he was kind of like, well, can we shoehorn kind of the operations of logic, things like this and that, this or that? Can we shoehorn these things into something like algebra? And there's a bit of a problem. You could say, well, yes, true is 1, false is 0. Okay, great. And is multiplication. It's false unless it's both 1 and 1. Then it's always false. The problem comes about with or, because it's like, well, it's 1 or 0. That seems like 1 plus 0. Great, that's equal to 1. But 1 plus 1 is not equal to 1 in ordinary arithmetic. So Boole kind of had to contort himself to make a Boolean algebra in which 1 plus 1 equals 1. And he did that. And things started to develop a little bit from that. There were various sort of mechanical, well, people like Lewis Carroll, Charles Dodson was big in sort of promoting symbolic logic and wrote textbooks of symbolic logic. This was kind of a follow-on to Boole ideas. And then there were little machines that were built. Was Jevons, Stanley Jevons, I think, was one person who built such a machine. There's another well-known person whose name I now forget, who also had built machines in the 1800s that were kind of logic machines trying to implement Boole's ideas. So those were known things. They were kind of novelty items. They were not part of engineering practice. Now, the truth is that I would say different countries, there was a different level of formalization of engineering practice. In a country like France, there was quite a lot of commonality. There were mathematicians who were being engineers. I would say that was probably less true in England, for example. It was much more people like James Watt, who, among other things, invented ideas like control theory, ideas like governors and so on. That was not, I don't think he thought of himself in any way as a mathematician, even though he was doing kind of mathematical kinds of things. So I think that was kind of a bit more of a divide between engineering practice and kind of theory. Now, Babbage was trying to make a computer that would print mathematical tables, that would print tables of logarithms and things like this, or more specifically, would print kind of values of polynomials that were approximating different things you might want to approximate for navigation, for life insurance, whatever else. The thing that so he never really got into the idea of building logic into his machine. Ada Lovelace, who I think understood sort of the kind of the objective of the analytical engine, which was originally kind of we will print different kinds of tables of polynomials. I don't know whether she understood kind of the fact that there was sort of a logic that could be applied. I mean, she was talking about things like, famously, she has a sentence, the analytical engine will weave algebraical patterns as as Jacquard's loom weaves patterns of pictures of birds and flowers. So she was thinking about it as algebraical patterns, I think. I mean, she talked about applying it to the composition of music. She talked about applying it to the computation of things like the three-body problem in celestial mechanics, solving the equations for that. But I don't think it was a story of logic as such. Now, what happened by the time, so in the early part of the 1900s, there was sort of the rise of electromechanical devices. I mean, electrical devices, people like Faraday have been around in the mid 1800s, and there are lots of sort of electrical kinds of things were developing. People like Charles Whetstone, later on, well, Maxwell and Hertz and things by the end of the 1800s. But the idea that sort of there will be electrical machines, well, obviously Edison and transformers and electrical supply and so on, this was very much a thing by the beginning of the 20th century. And people were certainly connecting all kinds of circuits and knowing that, you could have switching this to that and so on. That was certainly part of electrical practice. The idea of formalizing that and the idea of sort of switching networks that were formalized, well, it didn't sort of mathematicize until Claude Shannon's master's thesis, I think, in the 1930s. Now, it will have been the case that there were increasingly sophisticated electromechanical switches used particularly for the phone system that were coming into play. And I think, and also to some extent for calculators, but more so for the phone system. And there must have been knowledge, there were crossbar switches and so on. There must have been some knowledge of the fact that that was sort of a logic-like thing. I would say that it was that was by the time of the Second World War and the construction of things like the code breaking stuff at Bletchley Park in England, that was all kind of electronic switching systems that had come from the phone system. Again, I don't think they even thought about it, even at that time, as a story of logic. They thought about it as a story of kind of filling in different features of some kind of possibilities, combinatorial possibilities for breaking a crypto system. I don't think it was like, this is general logic. In fact, at the time of early electronic computers, again, it wasn't really a story of logic as such. The idea, when John von Neumann was writing about, how should you build computers, he was talking about different kinds of organs. And those organs, in a biological sense, those organs were logical organs, things like and or and so on. And I'm kind of thinking that that was how kind of the notion of logic like that came into the construction of electronic computers. Because I think in things like the ENIAC and so on, that the real focus was on doing arithmetic operations and maybe doing some conditional branches and things like this. But that was not really the this and that and so on. But that was certainly something that was in, von Neumann's work in the 1940s and beginning of the 1950s on computers. Let's see. Susan asks, if you could redesign human language from scratch, what would you change? Well, that's been tried a bunch. In the late 1800s, things like Esperanto were kind of brought in as more regular and more international versions of human language. It didn't catch on. I mean, I remember when I was a kid, particularly at like Heathrow Airport in London, there would be signs in, English and French and German and whatever, and Esperanto. And I was a bit sad when some new terminal was built or something, and the Esperanto signs went away. That was probably maybe in the 90s, the Esperanto signs disappeared. Esperanto never really caught on. Why was that? Well, really, it's because the tide of English kind of took over, and English became the de facto international language, and there wasn't really a need for something different. And I think, Esperanto was all tied up. I think the word Esperanto in Esperanto means I hope. Um, and it was very much tied up with sort of an internationalism movement and a kind of a world peace movement and so on, which probably didn't survive the among other things like the First World War and so on. I think that um, so one might hope that having a language where kind of everything is phonetic, you can spell easily, that might be a nice thing to have. It's kind of, English has these weird design hacks where people tried to burn in kind of the meaning of words into their spelling in very weird ways. Like a famous example is debt, D-E-B-T, which comes where the B is not pronounced. And I think in earlier English it should have been spelt D-E-T-T, but somebody had the bright idea that, debitor and so on from Latin, let's burn that meaning into the spelling, but not pronounce it, which is sort of a design mistake in English that one could expect to, one might not want to have. And obviously languages where the written form came after where the written form came after the spoken form, you don't have things like that. I think in Russian, for example, it's mostly phonetic in spelling, which makes the spelling bee competition less interesting, so to speak. But I think there are features like that in English. I think different languages have different, as I say, different ways to do things. There've been a whole rash of conlangs, constructed languages that have been made, I think, more often as art projects than for practical purposes. I mean, whether it's Klingon or Dothraki or one of the other languages that's been made for some movie or television show or something like this, those are constructed languages which are, in a sense, artistic languages. There are also languages which have been made, again, somewhat as art projects, languages like Ithquil, which is sort of the most complicated constructed language that tries to sort of put all the functionality of all languages into one language, or things like Toki-Pona, which is a very minimal language, which if it didn't have kind of the kind of morphological structure of something like Finnish, would probably sound like baby talk. But that's a kind of a minimal language. I think this idea of, can we make a constructed language that's better than languages we have? I know people have imagined that, learn to speak Ithquil, which has everything built into it, and sort of the Sapir-Whorf hypothesis will take you to better thinking. I don't think that's convincingly worked out, but that's the kind of thing one can imagine. Now, I think it is a thing that's worth understanding. In human languages, there seems to be pretty good translatability of most things between most languages. I mean, there are languages that are spoken, used in places where people just don't have a particular kind of thing. They don't have snow on the equator or whatever else. Well, maybe they do in a mountain, but so there's more and less need for different concepts in different languages. So there are things which are a bit hard to translate because those concepts don't exist. And there are kind of nuances, cultural nuances, which don't really come with the language, they come with the culture, which has been expressed in a language, and those are sometimes hard to translate. But fundamentally, there's decent translatability between human languages, and there's sort of so they're all sort of equivalents at that level. And if you can think in one language, you can think in another language, probably, with some nuances, mostly cultural, between them. In computer languages, it's actually a very different story, I think. I mean, having spent a lot of my life designing and building the Wolfram language, computational language, I can plainly see that there are concepts that, even for myself, once I've kind of crystallized them in our language, then I can think in terms of those concepts and sort of build towers with those concepts. But without having invented those things in the language, I'm sort of just not in a position to think in those terms. It's, one can imagine that there is a way of forming that thought as some kind of complicated, incoherent collection of nerve firings, but to make that thought coherent, to package it up so I can remember it, so I can build a tower based on that thought, so I can communicate it to other people. That seems to be a story of having to have some actual language, word type thing that comes from that. But I think it's something that people in the construction of languages, I mean, in human languages, there is people have long understood that there's sort of all kinds of political communication that, oh, you must say this rather than that. That's kind of a form of kind of changing the way the culture, the way society, the sort of politics of what's happening works. I mean, famously in 1984, what is it, Newspeak or something, is kind of a language that is intended to form the way people think about things. And it's certainly been attempted. I think it's been rather unsuccessful mostly in kind of, you should say this rather than that. I mean, I suppose there's a small amount of that in sort of modern American usage that has happened, but it feels like in the more dramatic versions of that have usually not in the end worked out. But when you're building computational language, it's because it evolves in a way that's really designed rather than something which sort of naturally evolves through usage, because it is something where it is the number one objective is you can communicate with your computer, not you can communicate with your fellow person. Although that is a secondary objective for us, it's something where you can just sort of from scratch say, this is how the computational language is going to be set up. And if you do a good job in that, you have a way to sort of scaffold people's thinking about lots of kinds of things, and it works really well. Now, I have to say, in my life, I've really done this more or less twice, once for SMP, once for mathematical and Wolfram Language, and I made a bunch of mistakes in SMP. I had a bunch of pretty decent ideas, I think, but it certainly was interesting to see, having designed and built SMP, seeing people use it. It was interesting to see what happened in actual usage. In actual usage, people, one example was I had these things called marks in SMP, and I remember kind of the main training documents about SMP had this sentence that said, marks are the enigma of SMP, which is, to a language designer, it's just you made a mistake in designing the language. People didn't understand that. I would say in language design, it's at some level sort of a strangely thankless task, because if you get the design right, it just feels natural to people. And if you get it wrong, people keep on, getting confused and asking questions about it and so on. And what is it? How does one get language right? It's kind of it's a rather difficult, almost artistic activity or architectural activity. What makes language feel natural to people? I think over the last 45 years, I've probably developed a certain amount of intuition about that. And I certainly can tell, we're thinking about putting some construct into Wolfram Language. It's going to be awkward. People are going to get hung up on that. And though there's another thing that's just going to feel smooth. It's going to feel like it fits into everything else that's going on. Some of that fitting in comes from the ambient use of natural language. Some of it, I suppose, comes from some kind of continuation of a sort of coherent strand of thinking that one develops in building up our computational language. Let's see. Okay, a number of other questions about language. Let me try and go through some of these, and then we have to wrap up here. Peter asks, which ancient civilization came closest to developing something like computational thinking? I would say the Babylonians. The Babylonians were systematizers. I mean, they had the forcing function of creating the first cities, and lots of things sort of had to get standardized and systematized when you have people sort of living together in a city and things get bigger, and you have to have kind of standardized, weights and measures and things like that. It can't just be, I know my friend Fred picks up, is giving me 3 hands worth of barley or something, and that's this. It has to be sort of standardized if you're doing it across this kind of larger domain of a larger city state kind of thing. And I think in terms of the way that Babylonians certainly had algorithms effectively for describing kind of doing sort of astronomical calculations, things like that. They really had those kinds of ideas. I would say more so than the Greeks, actually. Greeks were much more, this is the principle of how it works. I would say much less on the step-by-step this is how to do it type thing. And then when when it comes to Roman times and so on, I mean, I think there was a lot of kind of this is how to do it when it came to military processes, when it came to various kinds of construction processes and things. But I don't think that was so much in the abstract domain. So I would say the Babylonians are probably the ones. Now, they were lucky because they wrote their kind of they wrote things down on clay tablets, which have survived. I mean, another civilization that where a lot has survived is the Egyptian civilization. It's my impression that there was a lot less kind of this sort of let's think sort of algorithmically about things. I mean, we don't have, the Egyptians clearly had design. We even know some of who did it as individuals, the design of the pyramids and things like this. But I don't think we have as much of the kind of this is the abstract algorithm by which you do this. We have a bit more of that in sort of the Babylonian way of thinking about it. And when you say abstract algorithm, it's not quite as sort of as procedural as one might imagine that to be. Just like the very earliest grammars were really just aphorisms. It works this way and this way and this way and this way, a bit like the templates for logic and so on. Let's see. I see asks, is there any truth to the saying that the American accent is the original British accent? This is so steeped in kind of national pride and socio-political kinds of things. I know when I lived in England, people were still feeling very superior, even though the British, by the 1960s and so on, the US was far the ascendant kind of country relative to England. I mean, that was a story from was at least 40 years old by that time, that the US had sort of surpassed Britain as a significant power in the world. I think that the thing that people used to say, but still there was a notion of British pride, so to speak, of we are the cultured, sophisticated country. Those Americans are just hick farmers out there type thing. And I do remember people saying to me with complete seriousness that, oh, that the American accent comes from the kind of the farmer's accent in Cornwall. Cornwall is kind of I suppose, is that sort of might have the role of something like Appalachia in US culture or something. And it's kind of it's the hick farmers in Cornwall. That's where the American accent came from. I suspect it's complete nonsense, but it was a sort of national pride kind of claim that was made. There's a question from Jamie here. Did scientific knowledge spread more through people or through written systems in ancient civilizations? I would say that it was a very people-to-people kind of thing. Things did get written down. I mean, for example, in the Library of Alexandria, things were clearly getting written down. But still, Euclid was teaching in the Library of Alexandria, which was basically a university. The fact that his works got written down, I don't know what the practice of what was happening, whether it was like you read the scroll first and then you go to talk to Euclid, or whether it was Euclid is giving lectures and somebody wrote down something from the lectures so they could remember it. A practice that in the US, at least, and I think in other countries, there were these things called ciphering books, which were things where when you learnt math in school, what you did was you wrote out this book of different kinds of math problems, the rule of threes, the rule of sixes, and so on, different kinds of structures of, this, which were all sort of templates for doing math. And people would spend, years of their schooling writing out these ciphering books, and then they would keep them as kind of textbooks. If you were going to be a farmer and you needed to figure out how you would do some kind of calculation with I don't know, compound interest or some land surveying calculation, you would pick out your ciphering book that you had written when you were a 10-year-old, 11-year-old, something like this. So that was kind of the practice. And I think it could be that the written works we have from Euclid were somebody writing things out in that kind of way to remember for themselves. It is my strong impression that whether it's Plato's Academy or the Library of Alexandria, that it was like humans were teaching humans rather than sort of offline textbook reading. I don't know whether that's known for sure, but that would be my guess. Um, let's see. Well, I think I should probably go to my day job. Somebody is commenting that it is Ada Lovelace's 210th birthday today. Um, her original birth was um, uh, kind of a curious and almost scandalous thing. Her father, um, Lord Byron, George, oh my gosh, what was his last name before he was Byron? Oh, I don't remember. But anyway, became Lord Byron, was a celebrity poet, and a celebrity who, that was her father. Her mother was a person called Annabella Milbank, who was a rather straight-laced kind of later activist reformer type who quite how she had gotten together with Lord Byron was a strange thing, and things fell apart before Ada was born. Um, Byron was quite the playboy. Annabella Milbank was quite the straight-laced person. By the time Ada was born, Byron had left England. He never saw Ada in person. He had apparently a locket with a picture of Ada with him, but he never saw her in person, never met her. And the I think the main obsession of Ada's mother was to prevent Ada from going the way of becoming a crazy poet. And so that was part of why she pushed for Ada to learn all these scientific kinds of things. I mean, they lived in a country house, and as was the tradition of the time, Ada was kind of homeschooled, and she was always getting kind of sort of tutors in areas like mathematics and so on to avoid Ada becoming a poet of any kind, even though later on Ada would describe herself as a poetess of science. Um, and Ada's sort of her contributions were particularly in sort of condensing ideas in the way that sort of a poet philosopher might do. So that was how that went. But I think the turbulence of Ada's birth sort of reverberated for well over a century as the kind of supporters of Annabella Milbank and supporters of Byron kind of duked it out with books written by each side and so on, talking about the shocking features of each side. And I think Ada got somewhat caught up in that, and there was lots of scurrilous things said about the later Ada as a result of that kind of the supporters of Byron were always trying to sort of character assassinate Ada as a way of kind of character assassinating her mother. I mean, her mother outlived Ada. Ada died quite young of probably cervical cancer, and the her mother was always, I think her mother was a somewhat difficult character. I mean, she was always explaining that she was very sick and so on, even though she lived to a ripe old age, and was always kind of using that as an excuse for different kinds of things. Although the one thing that perhaps Ada's mother did contribute to the course of intellectual history was that she took Ada as part of her kind of reform society thing. This was a time of the Industrial Revolution and what were later described as the dark satanic mills of northern England. Um, she she took Ada on a tour of the mills, in which when Ada was probably 15 years old, maybe, and Ada had the chance to see all this machinery. And that was the same kind of machinery and the same kind of ideas that ended up being used by Babbage in his difference engine and later analytical engine. Ada had seen that kind of machinery by being toured around the mills, I think more for sort of reform purposes than other things. I mean, Ada's mother had started a school, for example, and various other things. Anyway, much to say about Ada. Always an interesting topic. I think She would have been interesting to meet. I think a mixture of a British society person with a math nerd, and quite uh, um, a spirited person, I think. Anyway, I should wrap up there. I think I have a day job live stream coming up right now. But thanks for joining me, and talk to you another time.